Hi everyone, I'm Elahe. Nice to meet you virtually, everyone, and sorry for not being able to attend in person. And thanks for the organizer to giving me the opportunity. Uh, I'm Elahe Arani, head of AI research at Wayve, and today I'll be sharing our latest work on how we are approaching generalization and safety in autonomous driving. Okay, great. Then let me begin with the foundation of what we do at Wayve. Our mission is to reimagine autonomy through embodied intelligence. And that basically brings us to something that we believed so hard that that autonomy cannot be hand-coded, nor it can rely on a brutal heuristics. And it must be learned through experience in the world, just like the human do. And since 2017, we pioneered a new approach for embodiment, and that's an end-to-end approach, what we call it AV 2.0. And basically that means that learning a general purpose driving intelligence through this end-to-end neural architectures. The reason is simple. Traditional autonomous stacks struggle to scale. They needed to a lot of label data and so many different sensory stacks and also HT maps, and it made them economically not very viable to long tail scenarios and scaling to the new geos. Autonomous driving is often framed as a robotic problem or system integration challenges in the past, but fundamentally it's an AI problem. Specifically, it's an embodied AI problem. As you see in this very example, that every scenario is so unique and can be very different. Basically, autonomous driving needs to make complex, uncertain, and interaction with the words. And basically, it's not static, it's social. You need to negotiate with all the other road agents, and it's dynamic. It requires forward reasoning. And what we need here is to predict, plan, and adapt for these future changes. Let me show what this capability could look like. We started from London, very hectic roads, and we moved to San Francisco. We moved to Germany, urban and also more scenery side of cities. And this is how we believe that embodied intelligence with end-to-end approach can scale to 100 cities much faster than the conventional approaches. For the interest of time, I'm going to skip the rest of this video, but you can see it on our website if you are interested. Sorry. Yeah. To create a product ready for the autonomous safety, we basically need adaptability, safety, and trust. And these three pillars are not disjoint. They are tightly interlinked. And what does it mean is that we cannot build a trust with a system that doesn't have safety. And you cannot ensure safety if the system cannot adapt to a new environment and new platforms. Basically, generalization can unlock both of these at the same time, adaptability and safety, so can bring trust as well. If you have a system that needs to re-engineered or relabeled every time that we change a street, vehicle, or a city, it's not scalable, and it won't be safe in the edge cases and these rare cases that we are facing in the autonomous driving. We believe the real benchmark here is not that does this work here? Basically, instead we need to say that can it adapt safely everywhere? And that's the transition from prototype to real world deployment. Let me break down how this vision translates into real world deployment for us at Wayve. What we have is that our systems can work with lean and very flexible ABS stacks. It's sensor agnostic. You can use as less as just cameras, or even add more expensive sensor stacks, and it doesn't need HT maps, and basically can adapt to any new environment and in new road only by seeing some extra data, and therefore can generalize to these situations better. And also, what we are designing here, it's from both assisted and autonomous driving, from L2 urban to L3 highway. But what it's more fundamentally, this is the foundation to get to the full autonomy. Wave expansion to US for us wasn't just a geography milestone. It's a key demonstration of the AV 2-point approach to autonomous driving, basically the generalization power of this approach. Powered for a foundation model that trained on a global training set, our embodied AI adapts to this new geography and new vehicle types with minimal additional data. With only 100 hours of data, we get 5x better performance for this intelligent driving. And then with additional 400 hours of data that was collected over 8 weeks, that went down to 40x, basically. And this shows how this problem is not an engineering, but it's an AI, it's a data problem, and the AI system can very easily adapt to the new environment with a minimal data available to them. Adding data from more markets, sorry if the voice is a little bit annoying, I can stop it actually. Adding data from these new markets, actually from UK and US, made even generalization on already seen environment better as well. It's basically backward transferability is also there, as well as forward transferability, that it's at the adaptation and generalization on the new scene, it's getting better. And let me show you a few zero-shot driving performance of our driving models, that not just driving on the left and right side of the road from UK and US, but we got those models into Canada, in Vancouver, you see the top row, and then into Japan, in Asia, the bottom row, you see all these are very unique scenarios out of distribution and completely new to our models. The engine behind these capabilities are the foundation model. Basically, our end-to-end neural architecture trained on petabytes of a diverse set of data collected from our own internal fleet to our partners. And it's agnostic to vehicle types, the different geos and sensor configuration. The foundation model acts as a universal backbone for us. This model encodes basically very rich, transferable driving behaviors, and these are bootstrapped everywhere, basically. This adaptability or generalization, that it's well known, it enables to apply, basically to apply learned knowledge to an unfamiliar driving situation and enable safety by the design. But like any other common with every AI models, basically, there are still challenges. These challenges are coming from the data, especially for self-driving. We have safety critical and edge cases. We are facing long tail scenario distributions, and we need on-policy data. And the second one is evaluation. We need to safely, in a very safe and repeatable manner, being able to measure the improvement of our driving intelligence, and can trust on these rare cases. Basically, you can generate new cases. What we believe is the answer to overcome these challenges is the world models to use as a simulator for synthesizing data for training and evaluation of the for the driving models. Real world data only comes basically only accounts for a fraction of the edge case scenarios that we would like to have. We think the world models can bridge this gap and allow generate orders of magnitude more data of these cases. And this data can be, this approach can be data driven, it's scalable, it's reactive, it's interactive, and you can simulate full environment, and you can close the domain gap in perception and behavior as well, and you can control over the long tail scenario generation. Gaia 2, our next generative video. Okay, I don't know why the video is not playing, but anyway, this is our next generation of video generative world model that tailored for global autonomous driving. And with this, we enhance the controllability and the diversity of the vehicles and geo that we are covering with the new Gaia 2 over Gaia 1, and basically handling multiple camera viewpoints, diverse road condition, and critical corner cases that we couldn't do in the past. Moving from Gaia 1 to Gaia 2, you can see both are starting from the same scenario, but one is in much higher resolution and multiple cameras. You can see the spatial temporal consistency between this video generation from Gaia 2, that it's not only working with one camera, but it's a 360 camera rig across multiple vehicle platforms. And you can go from one vehicle to another vehicle, from one geo to another geo. And also we can control these behaviors. The world model is the Gaia 2 has a latent diffusion model operating in the latent space. And basically it trained to denoise partially noised input, latent conditions on cuboids to control the dynamic agents, embeddings, and the metadata to control environmental factors and the road behaviors, and also actions to control the ego vehicle and the camera geometry to simulate multiple vehicle platforms. The world model is trained on multiple tasks, such as starting from scratch, basically, based on any conditions that I mentioned just right now. We can ask the world model to imagine something and generate from scratch, or even roll out and getting some context from, and then generate the future of that context, and basically predicts the future on a temporal horizon much larger than what the model was trained for. And Gaia 2 simulates this full environment and embodied platforms. You can see here from the flags of the countries on the corner of the images. Each row is the same scenario. Basically, we start from the same scenario, and then the same road behavior is simulated into different platforms and geos. You can see it goes from UK to Germany to US, and then from day to the night. But the road behaviors here is very similar across all these. Let's move to more long-tailed scenarios and the safety critical scenarios. The example here you can see is the pre-collision scenario, condition where a collision might happen. Basically, we are giving that, and then the model can generate that data for us. And based on that, we can generate multiple magnitude of similar data with changing the weather, the time of day, any environmental conditions, and the number of agents and the interaction with the other agents that are in the scene. Another class of these critical behaviors are the emergency. Can you see my screen? No, sorry. Okay, the video doesn't play again. Another class of this emergency vehicle, emergency braking, basically. A leading car, you can change the behavior of these other dynamic agents of the road, and then basically generate this emergency braking. And then by that, maybe in your training data, you have a handful of those examples if you are lucky, but then you can generate a very diverse set of those examples across different geos and the vehicle platforms to train or evaluate your models later on it. This is another example for aggressive cuttings in the road. You can see from going from two agents from both sides here, a motorbike and a car. From left and side, they are cut in the road, and here it's a van. Basically, all these scenarios can be engineered, designed, and used for evaluation or even training of your driving models. Something else that our Gaia 2 is able to do is that given this existing real-world edge case scenarios, we can create the video, we can basically compress the video into high-dimensional embedding vectors, and then condition on this embedding space to generate multiple new scenarios, an infinite number of similar edge case scenario from that. Here is an example. The top row is the real video, but then the rest of the rows are the generated scenario. All of them are exhibiting the same high-level behavior, basically overtaking a bus here in this scenario. And then you can do it across different environmental conditioning for the model. Another example here is the top row again is real data, and the rest of them are generated by Gaia 2. The similar conditions on the embedding vectors, from that you can see it's all of them. The cars are both sides. The car starts from a stop, and it's very similar. And you can go from a twilight to night to the daytime, from Germany, from UK to US and Germany, across different geos. Basically, you can replicate the same behavior. Let's show some fun examples as well. These are very extreme out of the distribution generalization. And you can see we never had any sample data from the basically forest or driving into the woods. But here we are able to generate that, and the model can even basically know how the bushes and the branches are moving. This is completely out of distribution. And another extreme out of distribution is something that we have never seen, to drive into the ocean. It might be useful at some point for driving the models, but these are more like a fun example for us to measure the generalization power and controllability over this scenario synthesizing, basically. I think I went too fast, but to summarize is that driving is an AI problem for us, and generalization and safety are two sides of the same coin. Driving Gaia 2, basically, it was a new generative word model diffusion based, and we use it for synthesizing data in a more semantically meaningful and a scalable manner for controlling over the scenario generation, mostly for safety critical scenarios. And this controllability is applied across different domains and platforms. We can go from vans to the sport cars to the normal cars, and this we believe is a foundational capability for embodied intelligence. Sorry for going too fast. I think some of the videos didn't work, but I would be happy to take any questions.
All right, so if we have any questions for the speaker, please go up to the mic here and she should be able to hear you.
And thanks for the talk. But this brings up the usual question of the how realistic this model is, right? So how big is the sim-to-real gap? And especially in the case of driving into the ocean, we know this is not realistic, and also in future, we're sure this is not the way how to do it. How good is the training on such generated scenarios?
Okay, let me repeat the question to make sure that I understood correctly. You're asking about how we measure the realistic aspects of these models, and this ocean example was an extreme example, and it's something that we haven't seen in the real data. Is that correct?
Yeah, that's, I guess that, but also for the other scenarios, how realistic are they? So they look realistic, but is the training on it also something realistic?
Okay, we are looking, while training the Gaia 2, we look at different metrics that they are basically very common across all these generative models, to look at the temporal consistency and the spatial consistency across different scenes. And also because we had the cuboids to condition on and many different kind of perception tasks that we run on these models, we can measure how visually the fidelity of these models as well. But these two examples, the bush, driving into the bush or the forest and driving into the ocean, both of them, as you can see, they are looking very natural. I'm not saying these models are 100% capable of coming up with any unseen and very extreme out of scene generalization, but they are quite capable. And for the use cases that we are looking to using mainly for creating this the emergency brakes, the overtaking, all these safety critical scenarios, or using the embeddings of our internal driving models to generate many more examples of this handful of safety critical scenario scenes in the scene, to go from one geo to another and from one platform to another. From, for example, if we use Mackie right now and the other day we want to use it on the van or another type of vehicle, it's very quickly generalizable, these models, and can with the high fidelity can generate and synthesize data for us. I hope I answered the question.
Thank you.
Yeah, okay.
Hello, thank you for the talk. Very interesting. I have a question. So this model has to essentially or implicitly learns a 3D representation of the world. So I'm wondering, have you tried running any experiments where you take the 5 cameras as input and maybe apply something like full map or a depth estimation model to get a 3D scene reconstruction?
No, we haven't tried yet on Gaia 2, but we are working on multiple, basically a specialized version of this for many internal use cases specifically, but that we haven't tried it yet.
Okay, thank you.
No worries.
Hello. Thanks so much for your talk. I was curious how you determined which edge cases to look at. Like, do you think about all sorts of different animals that might run into the road, children, plastic bags? I know that sometimes people will put salt circles around semi-autonomous cars. Like, how do you determine which of these edge cases to work with and think about ones that you might not have seen yet in your recordings?
That's a great question. I think it's a hard problem to. There are, I would say, many unknowns in that, creating those edge cases. If we know it, we could engineer or design a system systematically generate all those for us. At least the scenario generation on the high level, what would they look like? But for autonomous driving specifically, there are different benchmarks and the safety test, like NCAP, for example. You know some of those scenarios that are already classified and they are predefined. And you can use this kind of system to generate as many examples as you need to basically reliably measure the performance of your models and how trustable these models are for deploying on the real world, at least based on all the safety and the safety-based systems that the policymakers have come up with right now.
Okay, thank you. I would love to see models about tumbleweed blowing across because between New Mexico and Colorado, it's very scary sometimes when you're driving there.
Hi, can we have one more question? Sure. Yeah, thank you. Well, thanks for the talk. Just one quick question. I think because you've shown a lot of visual inputs to the vehicle, right? I'm wondering are you generating the vehicle commands at the same time? Because what you've seen are usually coupled with your vehicle commands, right? And then if so, how do you guarantee or ensure that's a valid and relevant trajectories for like the vehicle commands?
I'm not sure with the vehicle comments, what do you mean? Can you elaborate on that, please?
Yeah, probably what I mean is that what you've seen, right? You're seeing from the first person view, for example, of the vehicle. You put the camera in front of the vehicle, I guess, for like 5 cameras. But those are generated from what the vehicles are moving, right? And then are you generating the vehicle commands or trajectories at the same time? And then how do you couple them when in the process of your diffusion process, for example?
Basically, the system can go from generating examples from scratch. You can give condition-free or condition on any of those scenarios that you need, metadata or the embeddings or even the ego vehicle action or something like that. Or you can give the context. This context also can be only one camera for few seconds or even only 1 second. And then the model can generalizes to this multiple camera rig and also at the same time generate much longer context for that. But you don't need to specify these commands per camera. You only generate these comments from the front camera. This is what you want to see the agent coming, and then the spatiotemporal consistency across the other cameras with the front forward cameras are basically handled by the model itself.
Thank you.